So this is our last video about linear homogeneous equations. Remember, I've posted two kind of introductory videos which are just talking about the general ideas of why a linear operator is important and how they apply to solving linear differential equations. Then the next 5 videos, in which this is the last of those 5, we are discussing how do we solve the second part of our general method, which is the solution to the homogeneous equation L of y equals 0. So in the past 3 videos, what we've done is understood what the characteristic equation is telling us and how we can use it to determine general solutions of this equation, this homogeneous equation. And we're going to go over this in terms of second order, because if you understand the second order, higher orders doesn't really change anything. You're still using the same observations to determine the roots of the characteristic equation and how they interact to give you particular terms of your solution y sub h of the homogeneous problem. So that's really what we're doing now, is we're finding that function y sub h. Even though I'll be calling it y for these problems, it's really y sub h from our more general problem, which we're going to address in later weeks. So in the case that we have two real roots, r1 and r2, we have seen that by looking at linear operators and how the factoring of the characteristic equation translates into writing our second order linear operator as a composition of two first order operators, we realized that we could have just solved the two first order equations, and the solutions to those give us the two pieces of our second order equation. And our general solution is of this form. If the characteristic equation has one repeated root, r, so this is a case when the quadratic factors to something like r plus 2 times r plus 2, then in that case negative 2 would be the only root. So in this case, we get two terms, and we had to go back, and remember we were able to identify the first term of this just by the root and by method 1. But since we didn't have another root, we didn't know what the other solution would be. So we went back and took an educated guess, and then determined that by simply multiplying the first term, the e to the rx, by a power of x, we get the second term. And if you're in a higher order situation, we also saw that what happens in that case, if you've got a factor like r minus 5 to some power, you keep adding terms like this, and you keep increasing the power of x for each term. The final case was in the last video. We talked about complex roots. Using the quadratic formula, you can identify within the square root there's a negative number. When that occurs, you know you have complex roots of this form. So basically all you're going to do is split that quadratic formula, so you're going to have some number plus or minus the square root of some negative number. Basically that first number is your a, and then the square root without the minus, you evaluate that, and that gives you the real number b. And what we've seen by looking at examples is when this occurs, we can construct our general solution as follows. The real part of these roots a falls into the exponential, just like the roots did in cases 1 and 2 above. But the imaginary part, the b, introduces trigonometric functions into the mix, and that is what we're going to see later. Is this is going to occur when you're modeling something that's vibrating or oscillating, moving up and down or back and forth. And trig functions are functions that model such vibrations, so that's why this is naturally occurring. So let's look at 3 examples of initial value problems, one of each type. So 2 real roots. So we have our initial value problem, second order, linear homogeneous equation. We have 2 initial conditions. So we look at the characteristic equation. We realize that it has 2 real roots, negative 3 and negative 2. So we're in method or case 1. So our general solution is just a sum of these 2 exponential functions. And the constants are just there as placeholders until we apply the initial conditions to figure out what they are. Since our second initial condition does involve the derivative, we have to evaluate the derivative. This is just a simple application of the chain rule. Now these 2 equations are what we're going to use to plug in our initial conditions. So the first initial condition tells us that y of 0 is 1. So we take our equation for y, plug in 0 for x, and we plug in 1 for y. And that simplifies to this equation here. The second equation, we're saying that the derivative of y at 0 is 0. So we're going to take this equation, plug in 0 for x, and 0 for y prime. And that gives us the second equation. So we have two equations, two unknowns. There's many ways of going about solving this. Calculators will do it for you. But in this case, it's usually pretty simple. What you can always do is pick one of the equations, say this one, solve it for C1. And then you have C1 represented as some expression involving C2. Plug that into the second equation where you see C1, and now the second equation involves only C2. You can solve for it, and then once you have C2, you go back to either equation, plug it in, and then solve for C1. In this case, you find the solution is C1 is -2 and C2 is 3. So we just plug those in to our solution, our general solution here, to get the actual unique solution that I have here at the bottom of the slide. So anytime you get two real roots for a second order homogeneous equation with two initial conditions, this is basically what you would have to do. It's very simple. It's basically all algebra. You're not really doing much calculus except for differentiating the function y. Now one real root. Again, we have another initial value problem. Same thing, we look at the characteristic equation and we find its solutions. In this case, there's only one real solution, and it's 2, because this factors as r minus 2 times r minus 2. So we know we're in case 2. So we take our general solution as such, because the 2 is telling us that goes into the exponential functions. We just realize that because it's a repeated root, the second term is just x times e to the 2x. Again, we need to compute the derivative, because we have to apply the initial conditions. Do the same thing as before. In this case, it's very simple. Y of 0 equals 1. Letting x equal 0 makes this second term 0, so it's actually gone. So all we have is, we actually know what C1 is. C1 is 1. Second equation, we let x equal 0 and y prime equals 0. So 0 again, this term vanishes because there's an x there. So when x is 0, this is gone. So all we're left with is 0 equals 2c1 plus c2. But since we know c1 is 1, we can easily solve and figure out that c2 is -2. So plugging these into our general solution again gives us the unique, exact solution of this homogeneous equation with initial conditions. Finally, we go back to the complex root case. As with all these problems, you start with your characteristic equation and you look for the roots. By plugging this into the quadratic formula, you understand and simplify things, and you see that your roots are complex and they have this form. Some real number a plus or minus the imaginary number I times some other real number b. And in this case, those are 2 and 3. So we plug that into our solution, our formula for general solution in this case. Notice the 2 is the a, it goes into the exponential, and the 3 is the imaginary part, it goes into the trig functions. Again, we have to compute the derivative. In this case, it's a little more complicated, but it's just basic calculus stuff. Just look at this carefully. I've presented it in such a way that it's just a product rule. Product of this exponential times the product times the sum of these two trig functions. So I take the derivative of the exponential, multiply that by the sum of the two trig functions, and then to that I add the exponential function times the derivative of the sum of the two trig functions. And notice all that I've done here is the cosine term turns into a negative sine term, and then by the chain rule a factor of 3 pops out. For the sine term, the sine becomes a cosine, and then a factor of 3 pops out because of the chain rule again. So we still have our two equations, and then we can plug in our initial conditions. So y of 0 equals 2. Again, in this case, x being 0 makes the sine of 0, 0. So this vanishes. And the exponential e to the 0 is just 1. So this is just telling us that 2 is equal to C1. Second equation, again, you just have to look at it very carefully. If we plug in 0, the sign terms all vanish. This term vanishes, and this term vanishes. The exponentials themselves are just 1, because we're plugging in 0. So what we're left with is 2 times C1, because the cosine of 0 is 1. And then in this over here, we're just going to get a 3 C2. So 1 equals 2C1 plus 3C2. But C1 is equal to 2. So that's telling us that C2 equals negative 1. So now we can plug those in and get the unique solution to this initial value problem as follows. Again, whenever you're done solving some problem, it doesn't hurt to go back and check. Just double check that it's actually solving the equation. And again, we will talk more about this, but for now, this week, really all you're going to be asked to do for homework for the written assignments is to basically make sure you know what a characteristic equation is and know how to find the roots of a quadratic equation in all of the 3 cases, and then be able to translate that into a general solution. And then finally, be able to take initial conditions to determine the constants C1 and C2. So this week, that's all we're going to have to do. I will break that up into 2 separate assignments. The first assignment will basically just involve making sure you understand notation and what a characteristic equation is, and making sure that you can find the roots of quadratics so that we can apply it to these problems. And then in the second homework, I'll actually have you solve some initial value problems, just like these examples. And like I said before, I will also post 3 more videos from your textbook's publisher for each case as well.